We should start off by talking about what is a function. A function is nothing more than a rule with a name. The name we usually give it is f, although it could be anything. The rule tells us what to do with any input number. The input number is usually called x. And then the function takes this number, applies its rule to it, and returns to us an output number. We usually call that y. This is usually written as y equals f of x. So if f's rule is to add 2 to whatever number x we give it, we would say f of x equals x plus 2. So if f of x is equal to x plus 2, then suppose we give it x equals 8. It's going to give us back y equals 10. Since we set x equal to 8 in this case, we would say that f of 8 equals 10. By writing the function in terms of a variable x, we don't have to specify the output for every possible input. All we have to specify is the rule, so that if f of x equals x plus 2, then we know that f of 1 is going to be equal to 3, since adding 2 to 1 gives us 3. F of negative 12 is negative 10, because adding 2 to negative 12 gives us negative 10. Any number that we put in, 9,672,103.1, add 2 to that, we get 9,672,105.1. What is the domain of a function? The domain is really what numbers the function f knows how to apply its rule to. Since adding 2 to any number always gives us another number, this means that f's domain can include any number. We would say all real numbers. So let's change f's definition to f of x equals square root of x to see what happens. We know that as long as x is limited to 0 or to positive numbers, that f will work okay. But as soon as we put a negative number in there, we don't have a rule for taking the square root of a negative number. F cannot give us an output value y. If we give it x equals negative 5 or any other negative number, it's going to just give us an error. So we would say that negative numbers are not in f's domain. So a little bit more formally, a function's domain is the set of all values of x that the function knows what to do with. What values of x that it will give us back a number for. So for f of x equals square root of x, the domain is going to be x greater than or equal to 0 only. Let's look at the domains of the parent functions we've studied this year. The linear function f of x equals x gives us back whatever number we give to it. It can do this with any number, and so the domain is going to be all real numbers. F of x equals x squared. Now any number can be multiplied by itself, so again we will always get a number out for any number we put in. So the domain again is all real numbers. As we've seen already, f of x equals square root of x, we cannot take the square root of a negative number, so the domain has to always be a positive number, x greater than or equal to 0. For the rational parent function, f can divide 1 by any number that we give to it except for 0. Remember that division by 0 is always an undefined operation, so the domain is going to be all x except for x equals 0. The absolute value function gives us back the positive value of whatever number we give to it. It can do this with any number, so we can feed it any number x that we want. So again, domain is all real numbers. A number b can be raised to any value of exponent, including 0 and including a negative number. So the domain is all real numbers. Now the log function can only deal with positive values of x. We cannot take the log of 0, and we cannot take the log of a negative number. So the domain has to be all values of x greater than 0 only. One thing you can do to check domain with the calculator is when you do an operation, if it gives you an error, especially in a table, when you try to evaluate a function at a certain value of x, it's probably because x is not in the function's domain. So what about range? Well, we've seen that different functions can have different domains depending on what they know how to do with any number we give to it. Now this is important. As long as an input x is in the domain of f, f will give us an output y for that x. And so the range of a function is the set of all the possible y outputs that f can give to us. And that corresponds to all the x values that we can give to f, its domain. In other words, the range results directly from the domain. Let's look at the range of some of our parent functions. For the linear function, again, f gives us back whatever number we give to it. So if its domain is all real numbers, then the output, the range, must be all real numbers also. F equals x squared squares x, meaning it multiplies x by itself. So if x is positive, two numbers that are positive multiplied by each other will be positive. If x is 0, 0 times 0 is 0. And if x is negative, two negative numbers give us a positive number. So the output of this function can only be 0 or a positive number. So y is greater than or equal to 0. Now the square root function is a little tricky because we know we can take the square root of a positive number and get both a positive and a negative number. Square root of 25 is both positive 5 and negative 5. But when we want f of x equals square root of x to be a function, we can only have one output for each x input. That's what a function is. So usually we consider only 0 and the positive outputs of f, and we say that the range of the square root function is y greater than or equal to 0. For the rational function, even though we can put any number into f except for 0, no matter what number we put in, we will never get out y equals 0. For really big values of x, y is going to be very close to 0, but no matter how big x gets, y is never exactly 0. So the range is going to be all numbers except for 0. The absolute value function, again, that gives us back the positive value of whatever number we give to it. So the range is going to be y greater than or equal to 0. If we put any value of x into the exponential function, we're always going to get a positive number back. So for an exponential, the range is y greater than or equal to 0. For the log function, even though we can only put positive numbers in, we might get any number back out from the log function, all the way from minus infinity to plus infinity. So y is going to be all real numbers for the range. How do we get the domain and range from a graph? Well, if any given x value is in the domain of a function, we're going to have a point on the graph, and that point will be either above, at, or below the x-axis. So if you look on the graph below, the domain of that function is going to be all the values along the x-axis between the vertical lines, because there is a point on the graph above that line. In the same way, if a y value is in the range of a function, then it's going to have a point somewhere in that range of values for y. So if you look at the graph below, the red area shows where all those points exist between those two horizontal lines where it says range. You can imagine that we're projecting the points from the graph onto the x-axis and the y-axis, or even squishing the graph left and right, or up and down to get those two. Here's an illustration that kind of shows what we're talking about in an animation. If you look at the top, each point on the graph at the left is projected onto the x-axis. So each point projects downward, and we're going to trace that out on the x-axis on the graph on the right. And that's going to give us the domain of that function. If you look down below at the bottom, we'll do the same thing and project each point to the right or to the left onto the y-axis. And that's going to trace out the range of that function below. Let's look at the graphs of the different parent functions we've studied this year. This is the linear function, f of x equals x. Its domain is all real numbers, its range is all real numbers. If we put x into it, we get the same value x out. So if x equals 4, y will equal 4. Here's the quadratic parent function, f of x equals x squared. The domain is all real numbers, and the range is y greater than or equal to 0, all positive numbers. Its function is to square the number we give to it. If we give it x equals 3, it gives us back y equals 3 squared, or 9. The square root function is the inverse of the quadratic function. F of x equals square root of x has a domain of x greater than or equal to 0, and y is also greater than or equal to 0. Its function is to undo the quadratic, to undo the square. So if we give it x equals 9, it gives us back y equals 3. The absolute value function, its job is to give us back the positive value of whatever number we give to it. So if we give it x equals positive 3, we should get back y equals positive 3. If we give it x equals 0, it gives us back x equals 0. And as you see on the screen, if we give it x equals negative 4, we get back y equals positive 4. Its domain is all real numbers, and its range is positive numbers and 0 only. F of x equals 1 over x is the rational parent function. Now we can divide 1 by any number except for 0, so the domain is all real numbers except for 0. At 0, we have this dashed green line that represents a vertical asymptote. This tells us that the graph in purple is going to approach the green line but never touch it. This is because x equals 0, where the asymptote is not allowed in the function. We have the same situation with a horizontal asymptote at y equals 0, because no matter what value of x we put in, we'll never get a value exactly equal to 0 from the output. This horizontal asymptote represents a hole in the range. The exponential function that you see here has a domain of all real numbers, and its range is all positive numbers. It too has a horizontal asymptote at y equals 0 along the x-axis. All values of the graph will be above that line. The log function is the inverse of the exponential function. It has a vertical asymptote at y equals 0. Its domain is going to be all positive numbers. We cannot put 0 into the log, and we cannot put negative numbers. Its output, however, is going to be a range of all real numbers. It can extend all the way down to negative infinity and all the way up to positive infinity. Transformations are changes that we make to a function to transform it into a useful model of some real situation. For example, a ball thrown up in the air follows the path of a parabola, but f of x equals x squared must be reflected, shifted, and stretched to actually match that path. In Algebra 2, we focus on 4 transformations: reflection, which is flipping the graph over the x-axis; vertical stretch or compression, enlarging or reducing the graph in the vertical direction; horizontal shift, moving it left and right; or vertical shift, moving it up. Every function, no matter which one it is going to follow the same pattern with transformations. So we're going to have plus or minus in the front, an a value multiplied by the function with x replaced by x minus h, and to the whole thing we'll add k. The plus or minus determines if we have a reflection over the x-axis. If the sign is negative, we will have a reflection. If not, it stays at its original shape. The value of a determines the amount of vertical stretch. If a is greater than 1, the graph will stretch vertically. If it's less than 1, it will compress vertically. H determines the horizontal shift. If we're using x plus h, we go to the left. If it's x minus h, we go to the right. K determines the vertical shift. Adding k to the whole thing shifts the graph up, and subtracting k shifts the graph down. So we can apply this same general format to all the parent functions that we've studied. Now for the linear function, we're going to replace a with the letter m and k with the letter b. We use y equals mx plus b because those letters m and b are special names given to the line because of the line's special properties. But keep in mind that the slope m is really the same thing as a, and the y-intercept b is really the same thing as k. For the quadratic function, you see the form on the screen there. We also call this the vertex form because this shows us very clearly on a graph where the vertex of the quadratic parabola exists. Square root function, absolute value function, rational function. Now keep in mind here that we can have a either multiplied by the whole fraction, or we can move the plus or minus a on top of the fraction. You may see that either way. Exponential function and log function as shown. So if you compare each of those to the general form at the top of the screen, you'll be able to see that all we're doing is changing the look of the function, but all of the transformation letters are in the same place on each one of these. Remember that the domain and range will follow the transformation. If a function is shifted 3 units to the left, then a domain of x greater than or equal to 0 will shift to the left as well and become a domain of x greater than or equal to -3. Same thing with the range. If the range is shifted up and down, then a range of y not equal to 0 is going to be y not equal to 12 if the graph is shifted 12 units up. The same applies to asymptotes. Those asymptotes will also follow the transformation and shift by the same amount. Let's talk about scatter plots now. These are graphs of individual data points collected in the real world. Usually we try to fit some sort of a function into the data so that we can use the function to make predictions about the data and draw conclusions. When we do this, that's called regression. It's usually done on the calculator or by computer, but for some scatter plots, for lines especially, it can often be done by hand. And since many of the scatter plots that we work with are going to represent linear functions, we're going to put a line through the data, and that line is called a trend line. If the data on the graph tends to increase left to right, we would call this a positive correlation. If it decreases left to right, we call it negative correlation. And if no clear trend is visible, we say there's no correlation. So how do we find the equation of a trend line? Well, first we'll take the plot of the data and we're going to sketch a line through the data that seems to balance the points. Now this is a judgment call, and so one person's line may be different from another person's line. That's okay. We'll calculate m, the slope of the line, by choosing any 2 points on the line, x1, y1, and x2, y2, and calculating the slope using the slope formula. Please keep in mind that you want to pick points on the line. Don't pick data points. Pick points on the line because that's what we're trying to get the slope of. Then we're going to use the point slope formula that you see on the screen there to get the whole equation. x1 and y1 can be any point on the line. Certainly could be either of the 2 points that we've used to calculate the slope, and plug it in. So let's look at this example. Here's some data that was collected and plotted on a graph. First thing we'll do is draw a line through the data. Then we'll pick one point on the line. Looks like x equals 2, y equals 22 will be a good choice. We'll find another point on the line. 6 for x and 16 for y seems to be a good fit. Now we'll calculate the slope m. The difference in the y is 22 minus 16, and the difference in the x is 2 minus 6. This gives us a slope of negative 1.5. And so we would say that this graph has negative correlation. We're going to use the point slope formula by plugging in one of the points, and we'll use the point 2, 22. So y1 is going to be 22, x1 is going to be 2. We'll go ahead and distribute the negative 1.5, and then finally we'll add 22 to both sides, and we'll get the equation y equals negative 1.5 plus 25. This is our regression line, our trend line, and we can plug any value of x in to get a prediction for what the y value might be.